This session we are going to discuss about the summary of two-body central force problem. This is the part of the classical mechanics of J.C. Upadhyaya books, and I have made a simple summary of this whole chapter, that is the two-body central force problem. And now let's get started. In the chapter 1, let us take two particles having mass m1 and m2, and their position vector are r1 and r2. You can easily see that this is a two particle having mass m1 and m2, and their position vector r1 and r2. Okay, this is x-axis, this is y-axis, and this is z-axis. So we are going to discuss this theorem, all the concept in a short manner. Okay, so Lagrangian of this figure will be that is half m1 r1 dot square plus half m2 r dot square minus b of r. So actually Lagrangian is equal to kinetic energy minus potential energy. Here the kinetic energy is this part and potential energy is only v of r. So if we reduce this mass, this m1 and m2, and if r1 dot is equal to r2, okay, if r1 is equal to r2, this type, okay, so our equation will be this type, that is mu is equal to reduced mass, which is m1 m2 divided by m1 plus m2. Okay, hope you are understand. Here I can easily write that this is reduced mass, this is m1 m2 divided by m1 plus m2. So now let us discuss some example, that is in the hydrogen atom. In the hydrogen atom mass, there are electron and proton revolving around the nucleus. Inside the nucleus there is a proton and electrons are revolving around this nucleus. Okay, so the reduced mass can be calculated by m1 m2 divided by m1 plus m2 formula, that is me is the first mass of the electron and this is mass of the proton, and this reduced to, if we take common me, then 1 minus me divided by mp, and we know that the ratio between me divided by mp is 1 by 1836. So this is our final reduced mass of hydrogen atom. Now let us discuss what is the reduced mass of the positronium, that is me is the m positron atom. Here the mass of the electron and mass of the proton are equal, so we can take me is equal to mp is equal to m, okay, capital M. So we can write this m1 into m, that is m square divided by m plus m, that is 2m, and mm get cancelled out, then m by 2. For hydrogen atom, mass of electron is equal to mass of proton, and we can write this small m. Okay, so this also this same type. Okay, now let us going to discuss whether why the angular momentum is conserved. Okay, so in this session, first thing, the formula of angular momentum is that is r cross p, r cross m dot p. If we cross multiply this, okay, if we putting the formula of this formula, then we get this will be 0, so j will be constant, and in the field where f is equal to 0, this will be going into the conserve. When applied force is 0, then angular momentum will be conserved, because if f is equal to 0, then if applied force is 0, then angular momentum will be conserved, because f is equal to 0, that means dp divided by dt is equal to 0, and p is equal to constant, and constant means this must be conserved. Okay, and let us next is equation of motional central force and first integral. Here we have discussed the three motion, that is Kepler's first law, Kepler's second law, and Kepler's third law. Okay, so first, and we also have discussed about, we also going to discuss about what are the first integral of this chapter, okay, of this central force field. the particle which is under the central force field, what type of fast integral should be it deserve, we are going to discuss about that thing. So let's get started. This is f is equal to f of r vector divided by r vector divided by r. That means this is a unit position vector, and this will be minus del v by del r. Using polar coordinates, Lagrangian of the system becomes half m r dot square plus r square into theta dot square minus b of r. This if we put the x is equal to r cos theta, y is equal to r sin theta, then this formula can be derived. Okay, then p theta is equal to del l by del theta dot, that is m r square theta dot. And equation of motion we can easily find out from the Lagrangian, that is Lagrange's equation of motion, that is by putting this formula. This will be goes to 0, and we get this here, we get this. Okay, but this is a constant term, so we can take half from this side. Okay, and this m can be goes in right side. So this is not the problem, because m is a mass that is constant, and here also a constant, so not problem by writing this equation. So this is known as actually the aerial velocity. The aerial velocity of the particle is half r square theta dot square in the polar coordinate. Okay, and then next one is the differential equation for an orbit. For an orbit, equation of motion particle moving under central force motion, the equation is most important. Okay, then this equation also most important, that is j square u square by m into d square u divided by d theta square plus u is equal to minus f1 by u. Here you have to keep in mind that u is equal to 1 by r. Here j is equal to angular momentum, u is equal to 1 by r, m is equal to mass, and theta is the angle, and f is the function. Okay, so minus f of 1 by u, j square u square by m into d square u divided by d theta square plus u is equal to minus f into 1 by u. Okay, next is inverse square law. Okay, what is inverse square law? Generally v is equal to minus k by r is the inverse square law. So in the gravitational force, the formula is given by g capital M small m by r square. This is the example of the central force, that is the gravitational force and Coulomb force. So if we equate this gravitational force and Coulomb's force, then we get the f of r is equal to minus k by r square. Then f of r is equal to minus del v by del r, that is minus k by r square, and v. So v, if we integrate this, we get minus k by r. These are the example of the central force. Now we are going to discuss what are the direction of the force. That is j square a divided by mk is equal to e. Here e is the eccentricity. By knowing the value of the eccentricity, we can know what are the conic section. Conic section means what are the type of figures can be obtained by drawing in the graph. Okay, if eccentricity is greater than 1, if eccentricity is equal to 1, if eccentricity is less than 1, and if eccentricity is equal to 0. Okay, so by putting this formula, this is also the formula. The formula is 1 plus 2e by m into g square by k square or square root. Okay, iska square root. The square root of 1 plus 2e divided by m g square by k square. You have to memorize this formula. Okay, so you can do this. So if the eccentricity is greater than 1 and energy is greater than 0, then the conic section will be hyperbola. If eccentricity is equal to 0 and e is equal to energy is equal to 0, then this will be parabola. And if eccentricity is less than 1 and energy is less than 0, then it will be an ellipse. Okay, then if eccentricity is equal to 0, then this may be a circle or other thing. This approximately this is a circle. Okay, so we have discussed the aerial velocity. One more formula, that is aerial velocity half r square theta dot, and this will be also can be written as j by 2m. This is the second Kepler's second law, that is the aerial velocity. This is the inverse square law. Okay, this is Kepler's first law, which is this is 1 by r law is equal to 1 plus e cos theta minus theta prime. Now we are going to discuss what are the stability and closure of orbit under central force. How can we know that the orbit of a particle, if it is moving under the central force, which exists, or the orbit can be exist? By knowing this concept, we know that what type the possibility of the value of n which determine the possibility of the orbit. Okay, we total energy is conserved. We have know this equation, that is half mr dot square plus half j square by mr square. J is angular momentum, but these two term is ver. Okay, effective potential energy. These two terms going to ver, effective potential energy. This is central force potential energy, and this is normal potential energy. So fr, so doing this, we got fr is equal to minus kr r to the power n is equal to 1 n is equal to minus 2. If we put these two value, then the orbit are stable and close to orbit. Okay, then we got, after putting this n is equal to 1, we got f is equal to minus kr, that is the Hooke's law, and f is equal to minus k by r square, this is the inverse square law. Now simplify by, if we are going to doing some problem, then this formula must help us, that is r2, where r2 is greater than r1, that means r2 is maximum. R maximum by R minimum is equal to 1 plus eccentricity divided by 1 minus eccentricity. Similarly, velocity, if we compare the angular momentum, then we got this formula, that is v1 by v2 is equal to r2 by r1. Now let us jump to the satellite of the artificial satellite. Okay, the total energy in the artificial satellite will be half mvi square minus g m1 m2 divided by r plus h. Here r is the radius of the orbit and h is the height of the satellite from the surface of the earth. What is geostationary orbit? If the satellite rotates, time period of the satellite, if the time period of the satellite of revolution equal to the period of rotation of the earth, is called geostationary orbit. That means its rotation and rotation about the revolution, its revolution around itself, and the rotation about the earth will be same, that we call it geostationary satellite. The orbital velocity is r into capital G divided by r. R is the satellite orbit around the earth surface. Okay, and t is the time period, that is 2 pi r divided by v, that is 2 pi small r divided by capital R in square root of r by g. Now the last topic is the Virial's theorem. Virial's theorem, nothing more the 2 into kinetic energy plus potential energy is 0. I hope you enjoy this video in a great, and you enhance your concept about the central force problem. And if you like this video, must subscribe, and take care. Bye bye.